In this lesson, we're going to learn about using hypothesis testing to compare two separate independent groups and to try to determine if there's a statistically significant difference between them. And this is called two-sample hypothesis testing. So all of the 5 steps of the hypothesis testing remain the same. We're just going to be setting up the hypothesis a little bit differently because we're comparing two populations. Now, I want to stress this. I want you to remember that hypothesis testing is not about proving whether something is 100% certain. It's about using data to make the best possible decision based on probability. So, just like if you were in a courtroom and the jury sees evidence to decide if a person is guilty or innocent, we use the sample data to decide if we have enough evidence to support a claim about two populations. So nothing is ever 100%. All right, so just a quick review. All of the 5 steps are the same. Step 1 is state the hypothesis and alpha level. Step 2 is identify the test type and calculate the test statistic. Step 3 is using the rejection region. Step 4 is using the p-value method. And then step 5 is writing your conclusion. Now, the only thing that's going to change a little bit is the way that we write the hypotheses in step 1 because we're comparing two different populations. We're either going to compare means or compare proportions. In the first 2 rows, this content is the same, it's just written differently. So you don't have 4 different rows here. You have these 2 rows that are just written 2 different ways, and then you have these 2 rows here with information written 2 different ways. So if we're looking at 2 populations, population 1 has, we're going to call that mu1 for the mean of that population, and then the second population, we'll call that mean mu2. So if we're doing a left tail test, we're looking to see if mu1 is less than mu2. And of course, we're going to assume in the null hypothesis that they're the same. Now, we could write that a different way by saying if mu1 is less than mu2, if I find the difference between them and take mu1 minus mu2, because mu1 is less than mu2, then when I subtract those two, I'm going to get a negative number, which is less than 0. So this is just 2 different ways of saying the same thing. For a right-tailed test, our alternative hypothesis would be mu1 is greater than mu2. And then for a two-tailed test, we would say mu1 is not equal to mu2. And then, of course, you have the difference notation here in the second row that means the same thing, it's just written differently. Just like if you write 50% as 1/2. They both mean half, but they're written 2 different ways. Now, the proportion hypothesis are set up the same exact way. We just use p's instead of mu's. So just pay attention to whether you're testing a claim about a mean or about a proportion. In example 1, it says a study investigates if pregnancies involving single babies last longer than pregnancies with multiples. A sample of 35 single baby pregnancies has a mean of 39 weeks with a standard deviation of 1.5. And a sample of 30 pregnancies with multiples has a mean of 36.5 weeks and a standard deviation of 1.8. We're going to test this at a 5% significance level. So when I read this, I see that we're talking about 2 populations, pregnancies that involve single babies and populations where we're looking at pregnancies with multiple babies. So we're going to let mu1 be the mean of the population for the single babies, and we're going to let mu2 be the mean for the multiples. So looking back at the first sentence, we have a study investigates if pregnancies involving single babies last longer than pregnancies with multiples. So we're looking to see, we're testing the claim if mu1 would be greater than mu2. So when I write out my hypotheses, the null hypothesis is going to be that mu1 is equal to mu2. The alternative hypothesis is going to be that mu1 is greater than mu2, keeping in mind that it could also be written, since m1 is bigger, it could also be written that mu1 minus mu2 is positive, greater than 0. We have our alpha level that we identify from the information in the problem, that is 0.05. And because we're doing a greater than test, this is going to be right-tailed. Now, we're going to be using a t-test for two populations because we are not given the population standard deviation. We do have sample size is big enough to be able to do that. We have 35 for the first sample and then 30 for the second sample. Now, notice it does tell us we have a standard deviation of 1.5 weeks, but if you read it carefully, it's saying it's coming from the sample. It says a sample of 35 single baby pregnancies has a mean of 39 with a standard deviation of 1.5. So that standard deviation is coming from the sample. And the same thing goes for this standard deviation here for the 1.8 weeks. So because we don't have the population standard deviation for these populations, and because we have sample sizes 30 or greater, we can use a t-test for the difference of means. So to find in step 2 our test statistic and our p-value, I'm going to choose, it's a t-test for the difference of means, right? We're doing two means. I'm going to choose that option. Now, GeoGebra writes it as mu1 minus mu2, and then is equal to 0. We wrote it as mu1 is equal to mu2. These two are the same thing, because if mu1 is equal to mu2, then when I subtract them, I get 0. So that is equivalent to saying mu1 is equal to mu2. Now, we're doing a right-tailed test. So I'm going to choose this middle option. And then, of course, we don't use pooled. Don't ever check pooled in this class. And then we're going to put in the sample information for each one. Now, the first sample for the single babies, the sample size is 35. So I'm going to enter that in for N. The mean was 39. And the standard deviation was 1.5. For the second sample, we have a sample size of 30, standard deviation of 1.8, and a mean of 36.5. Now, when we enter all of that information in down here, you can see down here we got our test statistic. So let me put that in here. So our test statistic is 6.023. And our p-value is super, super small, where when it's rounded, it's 0. So we're just going to put in 0 there. For step 3, the rejection region, we're doing a right-tailed test. So we're going to be looking at the right tail. Now, because we're doing a alpha level of 0.05, this area in this tail where we want to find the cutoff point or the boundary for the rejection region, that's our value for t-critical. I want to make sure I go to GeoGebra and put in that information for the right tail and see what that cutoff point is. Now, because this is a 2-sample t-test, and we're dealing with degrees of freedom. Degrees of freedom for 2 samples is very complicated. It's not hard, it's just really messy. So I suggest to put in your degrees of freedom instead of worrying about calculating it by hand, to get the degrees of freedom when you run your test. So DF here is your degrees of freedom. So I'm going to write down, let's make another text box here. I'm going to put down that my degrees of freedom is equal to 56.6722. And I highly suggest that you use all the decimals, because if you round it too much, then you might get an error in your answer. Okay, so let's switch over to the distribution, because our goal now is to find that critical value for t and to find the cutoff point for that boundary. Now we're doing a t-test, so I want to make sure I'm using the student t-distribution. I put in my degrees of freedom here. So I have 56.6722. That's what I got when I ran the t-test for the difference of means. Now, typically, if it's one sample, then all you have to do is subtract 1 from the sample size. But it's a little bit more complicated when you're looking at a 2-sample t-test. All right, now I want to do a right-tailed, so I'm going to choose the right bracket to indicate I want it shaded to the right. And I'm going to put in that I want the area to be 0.05. So I find that my cutoff point for the boundary for the rejection region is 1.6722. So that means I'm going to reject HO if it falls in this red region here. So that means if the test statistic is bigger than 1.6722, then I'm going to reject. We're going to fail to reject if it falls in the blue area, which is where it's less than 1.6722. So now if I look at my test statistic to see where it falls, 6.023 is certainly greater than 1.6722, so it falls in that rejection region. So I'm going to say for step 3, we're going to reject HO. All right, now let's look at the p-value method. Our p-value is 0. Our alpha is 0.05. And 0 is certainly less than 0.05. So for step 4, I'm also going to say reject HO. So now when we write our conclusion, let's wrap our mind around what we're saying. Since we're rejecting HO, that means there is enough evidence to suggest that mu1 might be bigger than mu2. So we're going to say at the 0.05 level of significance, there is enough evidence to support the claim that, and then I'm just going to copy and paste our alternative hypotheses, because that's exactly what we're testing to make it a little bit easier. So at the 0.05 level of significance, there is enough evidence to support the claim that pregnancies involving single babies last longer than pregnancies with multiples. Okay, let's look at example 2. In example 2, it says, a study examines if the proportion of gas stations charging above $3 per gallon differs between Ohio and Massachusetts. In Ohio, 80 out of 150 sample stations charge over $3, while in Massachusetts, 92 out of 160 stations charge above $3. We're going to use a 1% significance level, and we're going to test if there is a difference in the proportions of stations charging over $3 per gallon between the two states. So for this one, we're just looking to see if there's a difference. We're not seeing if it's greater than or less than. We're just seeing if it's different. So we're going to let P1 be the proportion for Ohio, and we're going to let P2 be the proportion for Massachusetts. So when I set up the null hypothesis, we're going to assume for the null hypothesis that they're the same. P1 is equal to P2. But for the alternative hypothesis, what we're testing is to see if the proportions are different. So for that, we're going to set up P1 does not equal P2. And then we're going to state our alpha level, which is 0.01, and the fact that it's a two-tailed test because it's a difference. All right, now in step 2, we need to find our test statistic and our p-value. The only test that we have in this class to test for proportions is the z-test for proportions. However, we need to make sure that we have a big enough sample for both of these. So for both samples, we're going to take n times p and n times q, multiply them together, and make sure that they're greater than or equal to 5. And in fact, they are, so we can use the z-test for proportions. So I'm going to come over and click on my Statistics tab. I'm going to come down and I'm going to do a z-test difference of proportions. So for the null hypothesis, we're stating that P1 is equal to P2. That is the same thing as saying P1 minus P2 is equal to 0. We're doing a two-tailed test, so I'm going to choose the not equal to sign. And now I'm going to put in the information for both samples. So in sample 1 for Ohio, we had 80 out of a total of 150 sampled. And then for Massachusetts, we had 92 out of a total of 160. So down here, we have the test statistic, which is negative 0.7377. I'm going to put that in here. And then our p-value is 0.4607. Okay, for step 3, we're going to use the rejection region method. So we need to find our cutoff points for the rejection regions. And in this case, we're going to have 2 because we're doing two-tailed. So we're going to take that alpha level of 0.01 and we need to split it between the two wings. So we have 0.005 area in each wing. So we need to find our critical value by going back to distribution. And because we are using the normal distribution to approximate the binomial distribution here for proportions, I'm going to make sure that I'm on the normal distribution. My mean and standard deviation should be 0 and 1 because we're doing z's. And I'm already on the right tail, so I'll do the right tail first. So I have 0.005 for the area in the first tail. So that gives me a critical value of 2.5758. Now, the other side should be exactly the same, but negative, because the normal distribution is symmetric. So when I use the left wing, and I put in 0.005, I get the same thing, just negative. So I have negative 2.5758. So in this case, we have two critical values because it's two-tailed. We have plus and minus 2.5758. So if we look at the left tail, if I fall in this rejection region, it's because I'm less than negative 2.5758. If I fall in the rejection region in the right tail, it's because I'm bigger than 2.5758. If I fall in the blue area, if I fail to reject and I'm not in the rejection region, that means it's going to be between negative 2.5758 and 2.5758 positive. All right, now looking at our test statistic, we want to see where that falls. Negative 0.7377 falls between the two critical values. So we're going to say fail to reject or do not reject, however you want to say it. So our decision based on step 3 is do not reject the null hypothesis. Now let's use the p-value method to make sure we get the same thing using a different method. The p-value is 0.4607. The alpha level is, that was 0.01. Let me double check. Yep. Okay, so when we compare them, 0.4607 is greater than 0.01. So our decision for the p-value method is going to be the same. When the p-value is bigger than alpha, we say do not reject the null hypothesis. So we're not rejecting the null hypothesis, which means there isn't enough evidence to show that there's a difference between the two proportions of the gas prices in Ohio and in Massachusetts. So for my conclusion, I'm going to write at the 0.01 level of significance, there is not, because we're not rejecting HO, there is not enough evidence to support the claim. And then just for the sake of making sure we're wording this right, I'm going to put what we were testing. I'm going to copy and paste it down here so we get the wording right. At the 0.01 level of significance, there is not enough evidence to support the claim that there is a difference in the proportions of stations charging over $3 between the two stakes. Okay, last example. Example 3, a survey investigates if people who attend church regularly report lower stress levels compared to those who do not. In a sample of 50 churchgoers, the mean stress scale score was 3.5 with a standard deviation of 0.8, while a sample of 60 non-churchgoers has a mean stress scale score of 4.2 with a standard deviation of 1. We're going to test at the 5% significance level. So we're testing a claim about a mean here. We're going to let the population of churchgoers be mu1, be the first group, and then the non-churchgoers will be the group 2. So that will represent the mean mu2. So since we're trying to investigate if the people that go to church have lower stress levels, we're going to set up our null hypothesis as they're the same. And then the alternative is we're going to say that the mean of the churchgoer's stress level is less than the mean of the non-churchgoer's stress level. Now we're going to test at 0.05 level, And because we're doing a less than test, this is going to be a left-tailed test. So let's go over to our statistics tab to find our test statistic and our p-value. Now we're going to do a t-test for the difference of means because we are not told what the population standard deviation is here. We do have sample sizes that are large enough for this to work. So the sample sizes need to be over 30. So we have 50 in the sample and 60 in the second sample. So we have what it takes to use a t-test. So we're going to do a t-test for the difference of means. GeoGebra uses mu1 minus mu2 is equal to 0 for the null hypothesis, but as I stated, that would be the same as saying mu1 is equal to mu2. We're doing a left-tailed test, so I'm going to choose this option. And then I'm going to put in all the information from the samples. From sample 1, it says we have 50 churchgoers, and we have a mean stress score of 3.5, and we have a standard deviation of 0.8. For sample 2, for the non-churchgoers, we have a sample size of 60. The mean stress score is 4.2. And our standard deviation is 1. Now, when we look down here at the bottom, it says our test statistic, let's write this down, negative 4.0779. Our p-value is so small that when it's rounded, it's 0. And because this is a t-test, we do have to remember to write down our degrees of freedom because we're going to need that for the critical value. So I'm going to write down our degrees of freedom that's given to us right here. 107.8377. That's our degrees of freedom. Okay, so we've completed step 2. Now let's go on to step 3 for the rejection region. So we need to find our T critical. So I'm going to come over to the distribution tab and we're going to work backwards to find that boundary. We're doing a T test, so we're going to use a student T distribution. I'm going to put in my degrees of freedom, 107.8377. And since we're doing a left-tailed test, we are already shading to the left, so that's good. And I'm just going to put in that I want my area to be 0.05 because that's our alpha level. So our boundary point, the cutoff for our rejection region, is negative 1.6591. So we're going to reject the null hypothesis if it falls in this red region, which means it would have to be less than negative 1.6591. If it's greater than negative 1.6591, then it falls in the blue area, and we're not going to reject that. So now let's take a look at our test statistic. Our test statistic is negative 4.0779. So that is definitely less than negative 1.6591. So in this case, we are going to reject the null hypothesis. So that's our decision for step 3. Let's look at step 4. So for step 4, we're doing the p-value method. So p is 0 when it's rounded. We have our alpha level, which is 0.05. and 0 is definitely less than 0.05. So for step 4, we're also going to say reject HO. So now all I have to do is write my conclusion. So I'm going to say at the 0.05 level of significance, because we are rejecting HO, there is enough evidence to support the claim. The alternative hypothesis is that the stress of churchgoers is less than the stress of the non-churchgoers, so that is our alternative hypothesis. I'm going to copy that from the question to save me some typing. So at the 0.05 level of significance, there is enough evidence to support the claim that people who attend church regularly report lower stress levels compared to those who do not. So we went through an example of each type of hypothesis test for 2 samples. Here, we went through a right-tailed test with a mean. Here, in example 2, we went through a two-tailed test with the proportion. And then we did another mean test down here, but this was a left-tailed. And in all 3 of those examples, you can see that the steps for hypothesis testing is the same. We are just going to be setting up our hypotheses a little bit differently because we're involving 2 mu's or 2 proportions. So just refer back to these examples to see how to set it up if you need to. And there's also this chart up here that I provided at the beginning. Sorry if I'm making you a little bit motion sickness by scrolling up and down. So you can also use this as a guide as well for your symbols.